Hi everyone, my name is Nazanin Farahpour and today I'll be presenting our work on Reconfigurable Accelerator Compute Hierarchy, a case study using Content-Based Image Retrieval. This is a joint work between University of California, Los Angeles and Simon Fraser University. In recent years, we've witnessed the wide adoption of FPGA accelerators in data centers. They are most commonly integrated as I/O-attached or on-chip accelerators and used to accelerate a broad class of compute-intensive applications with high energy efficiency. But when it comes to communication-bound workload and applications interacting with in-memory or in a storage dataset, their performance and energy benefits are limited by the efficiency of the data movement in the I/O stack. A typical server workload comprises of compute-intensive and communication-bound applications. In fact, it is common to have variations in the memory compute requirements even within different execution phases of one single application. And content-based image retrieval is an example of such application. The bottom line is, to cater all these applications, commodity servers requires more than just a conventional acceleration. One promising solution is shifting towards a more data-centric compute model and moving compute units closer to data. The major benefits of this approach is higher aggregated bandwidth and higher access concurrency, decreasing the energy cost of moving data and alleviating the burden of host CPU by offloading part of the computation. There is a lot of interest in academia and industry for near data processing in recent years. Unfortunately, existing work focuses on benefits of near data processing solely on one level of the memory hierarchy, either cache, main memory, or storage, while the collaboration of these accelerators remains mostly unexplored. So could different near data processing accelerators composed into a meta accelerator or a compute hierarchy that could further benefit an application pipeline? And what would be a hardware-software infrastructure for such platform? In this work, we will present a multi-level distributed acceleration platform that has near memory and near storage accelerators in conjunction with conventional on-chip acceleration. And as a target application, we will use a billion-scale content-based image retrieval because it is a pipeline of several kernels with different compute memory requirements, which needs access to enormous amount of data, and its throughput is important to the user experience. Let me give you some background on CBIR system. CBIR identifies relevant images from large-scale image databases using the visual content of the query image. A typical billion-scale CBIR system consists of an offline and an online stage. During the offline stage, each database image is first represented into a feature vector using some feature extraction method, and then organized into clustering using indexing structures such as KD3 or K-means. During the online stage, user query images are transformed into feature vectors using the same method as offline stage, and then the indexing structure generated in the offline stage is used to retrieve a short list of candidate clusters that are likely to be closest to this user query. These candidate vectors are then re-ranked based on their computed distances to the user query, and lastly, the original images corresponding to the k-nearest feature vectors are retrieved from the database. So we focus on the online stage of the CBIR pipeline because it's both data intensive and compute intensive, and its throughput is crucial to the user experience. So let's look at the online stage only. For the feature extraction, we use deep convolutional neural networks and PCA to convert batch of images to a batch of feature vectors. And then we send this batch of feature vectors into a shortlist retrieval kernel, which is actually using a matrix multiplication and comparison to compare with all the cluster centroids that we got from the indexing of offline stage. And then for each individual query vector and its shortlist, we have to run re-rank stage so that we use KNN and nearest neighbor searching to find the closest feature vectors to the query vector. And then we retrieve the data based on those closest numbers. This table shows the memory requirement of a typical billion-scale CBIR system. We run the full CBIR application running on an on-chip accelerator, and we computed the energy distribution per component based on our energy model. The result shows that 79% of the energy cost after acceleration is due to the data movement. So if this application was properly mapped into a compute hierarchy, most of these data movement costs would have been alleviated. So in this work, we present REACH, a reconfigurable accelerator compute hierarchy that offers a broad spectrum of acceleration options. We will now introduce compute units of each compute level, as well as the global accelerator manager, and we will present the software stack used to program this system. Our on-chip accelerators and CPU cores and global accelerator manager, they're all tied together with a high bandwidth network on chip, which provides a cache coherent interface between all elements and the main memory. Compared to the other FPGA-based NDP accelerators, this accelerator has a higher clock frequency, more on-chip resources, higher bandwidth access to cache hierarchy, but when the working set size exceeds the cache capacity, the performance becomes limited. So this is most suitable for compute-intensive workloads or applications with frequent core interactions. Our near-memory accelerator is based on AIM, which is a prior work from our research group, and it is used to interface with the memory network and the commodity DRAM DIMM, and it makes it a non-invasive design to existing components in the system. Each AIM module contains an embedded FPGA and AIM bus interface that allows inter-DIMM communication, and it has a configuration filter for accelerator commands coming from the memory channel, and it has a memory access filter to forward memory responses to local accelerators, to remote accelerators, or to the host CPU via the memory channel. When we compare our embedded near-memory accelerators to on-chip accelerator, they are less powerful, but they have lower memory access latency and higher aggregated bandwidth when we use parallel instances of them. And they are more suitable for parallelizable tasks with large memory footprints. Our near storage accelerator also uses power-efficient embedded Zinc FPGA, but it has an on-chip DRAM buffer, so it would limit the number of I/O accesses to the attached storage unit. It could be used in disaggregated storage server as well as the host machine, and it has access filters that are used to send normal read-write commands to SSD while sending accelerator commands to the FPGA. These type of accelerators are most suitable for streaming-like applications that are simple but I/O-intensive tasks with limited data reuse ratio. The software stack of REACH is designed to minimize the programming effort of using the compute hierarchy. There are 4 main components in this software stack. First, accelerator templates. When a new kernel is designed and optimized for a specific compute level, the FPGA bit stream alongside the kernel-specific driver and the data flow graph is stored together as an accelerator template. These templates later are accessed by REACH runtime library to be deployed to a specific FPGA device. The REACH runtime library has a general accelerator API with uniform view of all compute levels, and it also has a GAM driver that translates template execute functions into communication packets to be sent to GAM. The REACH config file uses the REACH API from the runtime library and accelerator templates to instantiate the compute hierarchy. It registers accelerators to each compute level, create fixed buffers for each accelerator, and initialize the data from file system if needed, and it creates communications buffer between source and destination compute levels. And we have a user application which describes the flow of the application during runtime using APIs for initiating executions and data transfer. We decided to separate REACH configuration from the application side source code because it allows the user application to be as abstract as possible and be portable across different REACH systems and allow GAM to balance the hardware resources during runtime. Let's look at an example REACH config file in the next slide. For this config file example, we use a simplified two-stage CBIR that only has feature extraction and k-nearest neighbor search. We use only on-chip and 2 nearest storage accelerator for this example. And to remind you, the main goal in Reach is to limit data movement across the compute hierarchy. That is why it's important to allocate regions of the memory where data would be sedentary during runtime. We use create fixed buffer API to allocate these spaces. It is also important to allocate the communication stream buffers to establish connection between two compute levels. For instance, in this example, we set up a CPU to on-chip communication buffer with a peer-to-peer connection to send the image data to our on-chip accelerator. We also use a communication buffer between on-chip and nearest storage accelerator where we're sending the query feature results, and we use a broadcast mode for this communication. And we also have a nearest storage to CPU communication buffer, which uses a collect mode. The programming style of the config file is similar to OpenCL standard, where users can create buffers and streams and associate them with the accelerator's kernel arguments, similar to this example. Now, the Global Accelerator Manager has a one-time task of instantiating the specific compute levels in the compute hierarchy. During instantiation, GAM sends the FPGA bit streams to program each accelerator, and it sets up the memory regions for on-chip and near-memory accelerators by modifying the memory controller registers and setting correct access granularities for each of these accelerators. And this type of reorganization and isolation of memory space for on-chip accelerators versus near-memory accelerators decrease the inter-task access interference and overall increase the performance of both accelerators that are running concurrently. And it also allocates empty stream buffers for each compute level, which is basically a pair of queues allocated in memory space of both source and destination compute level. And it could have the three main types of pair, broadcast, and collect, as we saw in the example. During runtime, Global Accelerator Manager uses a simple scheduling queue, a progress tracking table, and a status queue interfacing the rest of the system. The rich host-side runtime environment creates a series of job requests according to the job description of the host application. The job requests are sent to GAM in form of accelerator command packets through the GAM driver, and GAM breaks each job into multiple tasks that may or may not be assigned to the same compute level. So GAM dispatches those tasks to the specific on-chip near memory or near storage queue and keep tracks of the running accelerators using a progress table. So when a target hardware is set free from a previous task, GAM invokes the next task from the queue by sending the command request to the target hardware. If a task is done, the returned status packet will have the memory region address for the output of the task to be forwarded to input buffers of all dependent tasks through DMA requests. So in summary, the GAM enables coarse-grained pipelining between different compute levels by allowing accelerators at different levels to work on different tasks at the same time. The accelerator tasks are initially designed to be small enough to exploit task-level parallelism, but large enough to amortize the data transfer overhead. We will now discuss the evaluation setup and the results. For our simulation setup, we extended the open-source Parade simulator to model accelerators with different frequencies, latencies, and bandwidth to attached memory modules. For our baseline system, we used an on-chip accelerator that is modeled after a Virtex UltraScale Plus FPGA, and for near memory and near storage accelerators, we used an embedded Zinc UltraScale Plus FPGA and used data from that to plug into the simulation module. The table here shows the three main kernels designed for our experiment: convolutional neural network matrix multiplication and k-nearest neighbor. It shows different implementation of the same application on Xilinx Virtex UltraScale Plus and Zinc UltraScale Plus, and it shows the utilization and the kernel frequency obtained. There are two numbers for Zinc FPGA power, which represent the power for near memory and near storage accelerator respectively. The near storage accelerator has a small DRAM buffer and interface that increase the dynamic power compared to near memory accelerator. To estimate this energy consumption, we used SDAccel post-routing power reports to estimate the power consumption of on-chip accelerator, and this report is further used along with Xilinx power estimator to estimate the power for near memory and near storage accelerator by adjusting the operating frequency, utilization, and onboard resources. We will discuss two primary set of results. First, the runtime and energy cost of each CBIR step using near memory and near storage accelerators, while the on-chip accelerator is our baseline. And the second set is performance energy consumption of the full CBIR pipeline when it's properly mapped to reach. For feature extraction, our on-chip accelerator uses a batched implementation, whereas near memory and near storage accelerator uses a single image for task and parameter duplication. Our initial network parameters for on-chip accelerator and near memory accelerator are preloaded into DRAM, whereas they are stored in private device DRAM for near storage accelerator. The dotted lines you see in the runtime and energy figure shows where the on-chip accelerator stands. Looking at the figures, the on-chip accelerator has a clear advantage because the feature extraction is a compute-bound kernel that benefits from the larger SPM and more PEs sharing the same parameters within on-chip accelerator. And our on-chip accelerator had a higher operating frequency and high bandwidth access to LLC. But we see that as we grow the number of instances in near memory and near storage accelerator, particularly when we go beyond 8 instances, the collective performance of near memory and near storage accelerator start to surpass the on-chip accelerator, but the overall energy efficiency stays better for the on-chip acceleration. For short-list retrieval, the on-chip accelerator performance is bounded by bandwidth of loading data from DRAM. So the near memory accelerator achieves better performance when there is 2 or more instances because of the higher aggregated DRAM bandwidth. And the near storage accelerator has a slightly higher runtime than near memory because the PCIe or SSD access latency is slightly more than latency of DRAM access. For re-rank stage, the data resides in the storage level. So the near memory accelerator achieves speed up as we increase the number of accelerators, but reaches a plateau due to limited bandwidth of the host I/O interface. On the contrary, near storage accelerator benefits from higher aggregated bandwidth of FPGA SSD instances and achieves much better performance and energy efficiency. Now, when we map CBIR pipeline properly to the compute hierarchy, we could see that an asynchronous running of the application in 3 levels helps us achieve 4.5x throughput improvement, while eliminating data movement between levels helps us reduce the energy consumption per query by almost half. And the query response time, which is important in real-time scenarios, also sees 2x improvement. So in summary, we propose REACH, a reconfigurable accelerator compute hierarchy that offers distributed computational power and minimalized data movement costs. At hardware level, we introduce GAMP for coordinating these compute levels and reducing inter-task memory access interference and provide asynchronous task flow control. And at software level, we introduce a uniform programming interface that decouples the system configuration from the user application, and it minimizes the programming efforts of using the compute hierarchy. By deploying a CBIR system on REACH and showing that a proper application mapping could eliminate unnecessary data movement, we achieved 4.5x throughput improvement and 52% energy reduction compared to conventional on-chip acceleration. And thank you for listening, and you can email me any questions you have.